All right, in this screencast, we're going to discuss how chemical equilibrium is described, kind of what chemical equilibrium is, what it means, how you write it, all the things that go with equilibrium. So physical equilibriums are reversible, and so we think about reversible reaction is a process that can occur in both directions. So you can have reactants to products, you can have products back to reactants. A lot of the reactions that we see just have an arrow pointing in one direction, and that means that all of the reactants completely react to products. So you end up with 0 reactants left over and 100% products in the, kind of once they reach that end point. But most reactions in reality exist in a little bit of an equilibrium between the forward and the reverse process. So we end up with a dynamic equilibrium where the rate of the forward process in a reversible reaction is exactly balanced by the rate of the reverse process. Equilibrium can favor products where it really wants to go to products and the reaction really goes, or it can favor reactants where they don't react very much. So you can end up with different concentrations of things, but once you reach equilibrium, the rate at which those reactions are occurring are the same, the forward and the reverse. It doesn't mean that you have the same concentrations of everything, just the rates are occurring at the same, or the rates are the same. So if I add 2 to 3 grams of sugar into 100 mils of water, all of it will dissolve with some stirring in a short amount of time. I wouldn't even have to stir it, but to make it happen faster, I'm going to stir it. I will end up with no residual solid sugar. All the sugar will be dissolved. So it will go from solid sugar to aqueous sugar. If I add 100 grams of sugar in 100 mils of water, not all of it will dissolve, even with much stirring. I am not going to get all of that sugar to dissolve in there. So over time, you observe that no further change in the amount of dissolved sugar occurs. Eventually, there's just going to be, the extra sugar is going to settle to the bottom and no more is going to dissolve. That's when I have reached equilibrium. That's an equilibrium situation. So my concentrations of my, so-called reactants and my so-called products are not necessarily the same, but it's just some molecules dissolve and others return to the solid state, and the rate that each process is occurring is equal. So that's where we would draw it as an equilibrium reaction. So you would have a forward reaction and a reverse reaction, and they would be happening at the same rate. So equilibrium can be described in a bunch of different ways, and one of which, and we're going to do a lab with this, but one of which is a solubility equilibrium. That's what I was just talking about. How much of the solid stays dissolved versus how much of it settles out of solution into a precipitate. So the KSP, when we see K, the capital K, that generally means that we're talking about some sort of a calculated constant. So the KSP, which is the solubility equilibrium constant, it can be used to determine how soluble a compound is. So instead of testing it out, I just look at the value. If the KSP is high, then I know that it is very soluble and a lot of it is going to dissolve. If it has a low KSP, then I know that it has low solubility and it will not dissolve very much. So I'm going to have to do something to try to get more of it to dissolve, or move on to a different material that will dissolve a little bit more. So equilibrium reactions. Chemical equilibrium is the state of a reaction in which the rates for the forward and the reverse reactions are equal. You don't start out in equilibrium. That takes time for them to develop this balance. And equilibrium reactions are just chemical reactions that do not go to completion. You don't go you don't end up with 100% products and 0 reactants left, or 0% reactants. You end up with some reactants left and some products, and every reaction is different. So they're also called incomplete reactions because you end up with some balance between the reactants and the products. So here's an example of the reaction of nitrogen gas and hydrogen gas to form ammonia. And you'll notice that this is an equilibrium reaction. So some of it becomes products and some of it stays reactants. So you mix these components at an elevated temperature. And by elevating the temperature, you increase the likelihood that they are going to collide. So some molecules will collide with sufficient energy, enough to break the bond that's holding the 2 nitrogens and the 2 hydrogens together. And then when you break that bond and they recombine, because there is something for them to bond to, instead of bonding back to each other, nitrogen won't bond to another nitrogen, or hydrogen won't bond to another hydrogen. They will both bond specifically to each other, the nitrogen and the hydrogen. They won't bond to ones that are like themselves. They'll bond to each other to produce ammonia. But the key is, in order to make this reaction go, you've got to have it at an elevated temperature. So at a low temperature, it favors the reactants. At a high temperature, it favors the products. So this is showing you the equilibrium reaction for it. Initially, the forward reaction is really fast, and you can see this. This is the forward reaction, and it's going to happen. The rate of the forward reaction is going to start out really fast, but then you notice it starts to slow down. The reactant concentrations are very high, and there's very little product being made. Like in the beginning, there's 0 product, and we have all reactant. So the forward reaction is very rapid, but as time goes on, it slows down. The forward reaction rate decreases with time because I lose some of these reactants as I make more product. Eventually, they're going to get to where the forward reaction and then this reverse reaction are going to reach a point where they're the same, and that's going to be the equilibrium. So the equilibrium occurs when the rate of the reactant depletion is equal to the rate of the product depletion. So the rates of the forward and the rates of the reverse reactions are equal. That does not mean the concentrations are equal. I can still favor products. I can still favor reactants. And that just depends on the individual reaction. But it doesn't mean that I'm going to end up with 50% reactant and 50% product in terms of their concentrations. So the next essential question is going to deal a little bit with how to calculate the KEQ, which is the equilibrium constant. So hopefully you'll be able to tell the forward reaction, reverse reaction favorability based on the KEQ value.